Okay, today we are going to study how to solve thermodynamics equations for solids and liquids. Previously, for pure gases, we can use specific heat. They are Cp and Cv to determine the change in specific internal energy or the change in enthalpy. So if you want to determine the change in specific internal energy, such as U2 minus U1, we can use specific heat Cv, T2 minus T1. If you want to determine the change in specific enthalpy, H2 minus H1, you can use specific heat Cp, T2 minus T1. So these are the two specific heat equations for pure gases. What if you have solids and liquids? The main difference between U and H is U plus PV by the definition of enthalpy. So if you have solids and liquids, what is the main difference between gases and them? Right, they are compressible. These ones are not. So they are incompressible, which means their volumes do not change with the temperature. Incompressible. Is that right? In reality, no, they change their volumes with the temperatures. However, the changes are negligible. So we assume that they are incompressible. The change, but still there are changes in volumes when pressure changes or temperature changes. However, the changes are negligible, extremely small. So we say practically they are incompressible. If they are incompressible, let's look at this enthalpy equation. What happened to PV if they are incompressible? What is this V? Specific volume. If they are incompressible, the specific volume V is constant. So H is going to be the same as U if they are incompressible. Then what is the difference between the first specific equation and the second specific equation? There is no difference. So when you have solids or liquids, there is only one specific heat, C instead of Cp and Cv. Because U2 minus U1 is the same as H2 minus H1 because there is no volumetric changes. So Cp is the same as Cv, so you can just say C. Theoretically, mathematically this is correct. However, in the field, between Cp and Cv, Cp are more widely used because most engineering processes are constant pressure rather than constant volume. So Cp is more widely used than Cv. So when we say the specific heat of solid or liquid, it is just C, but many people just say Cp. Okay, just for your information. When you hear, the people say Cp of water, Cp of some rock, or Cp of stainless steel, don't get confused. There is no Cv, just C. But people like to call this C as a Cp. That doesn't mean that there's a Cv for stainless steel. There's a Cp for stainless steel. No, there's only one specific heat for solids and liquids. That's all. Then how can you use this C? If you want to determine U2 minus U1, it is just C times T2 minus T1. But even because the people like to call this specific heat as a CP, so it's going to be CP times T2 minus T1. Don't get confused between with this CP. For pure gas, CP is only to determine H2 minus H1, but for solids and liquids, there's no differences here. So there's only one specific heat. Okay? That's everything. Then what we are going to do? We are going to solve a few problems together to learn how to use this specific heat. The first one is a 1000-watt ion. What is a 1000-watt ion? What does it mean? It means every second the ion is going to consume 1000 joule per second. That is 1000-watt ion, whose base plate is made of 0.5 centimeter thick aluminum alloy. We have the density and specific heat. You can see CP, just C. The base plate has a surface area of 0.03 square meters. So we have the base plate surface temperature and the thickness of the base plate. So if you know the thickness and the surface area, what can you calculate? The volume. And you know the density. So if you know density and volume, what can you calculate? Mass. Anyway, initially, the ion is in thermal equilibrium with the ambient air at 22 degrees Celsius. What does it mean? The initial temperature of the ion is at 22 degrees Celsius. Assuming 90% of the heat generated in the resistant wires is transferred to the plate. What does it mean? 90% of 1000 watts is going to be Q in. Determine the minimum time needed for the plate temperature to reach 200 degrees Celsius. So the final temperature is going to be 200 degrees Celsius. The initial temperature is going to be 22 degrees Celsius. Then what is our system here? Ion, resistant wire. What is our system? The easiest way, the simplest way to determine our system is to check what is the property changing in this process. Density change, specific heat, pressure, surface area, thickness. What is the property which is changing during this process? Temperature, 22 up to 200. Whose temperature? System's temperature. Whose temperature? The base plate. The base plate is our system. So we have this base plate. There's ion. I don't know, it looks like iron or something. Anyway, there's a resistance heater, resistance wire is going to provide heat into this base plate. So there's a heat transfer. Q in. How much heat transfer? 1000 watts. But 90% of the heat generated in the resistance wires is transferred to the plate. What does it mean? 10% is going to be lost to the air. So 90% of 1000, 900 watts is W in. Am I right or wrong? Wrong. Yes, right. Why? Why this is wrong? Q in is 900 watts. We know it is wrong. Then why? Think about what is Q. Right. It's not supposed to be watt. Then what is the right unit for this Q? Yes. What is the relation between joule and watt? Watt is joule per second. So if you want to determine joule, 900 watts times time. So to determine Qin, you need to multiply by time. How long did you turn it on? Delta T. So 900 watt times delta T is Qin, not 900 watt. Don't get confused between energy and power. Don't get confused between energy, work, heat, and power. Power is the rate of this, okay? In this case, 1000 watt is going to be the power. So we got Q in. We know there is no Q out, there is no W in, there is no W out. So it's time to write the only equation we know. What is the only equation? Energy balance equation. So what is the energy balance equation? Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work. What is Q in? Oh, we just found 900 watt times time. Is there energy transfer by work? No. Is there energy transfer by heat from the system? We already, took into this account. So 1000 minus 100, so 90%. So this has been already taken care of. So the net heat transfer to the plate is going to be 900 watt times time. What is the moving boundary work for the alumina block? What is the definition of moving boundary? The work associated with volumetric change. So what is the volume change? So iron was this small, and after using it, it becomes like this big. No, that doesn't make sense. What is the volume change? Incompressible, right? So there is no volumetric change. What is the moving boundary work? There is no moving boundary work. Since there is no volumetric change, then 900 watt times time is going to be mass times U2 minus U1. Oh wait, we studied how to determine U2 minus U1. By how? Specific heat T2 minus T1. Specific heat T2 minus T1 times mass. So the equation is going to be 900 watt times delta T is going to be mass times specific heat times T2 minus T1. Do we know the mass? Or we don't? Then can you determine mass? Yes, we can. Because what? Because we have the density of this aluminum alloy 2770, and we know the thickness and surface area. So the density, the mass is going to be density times volume, and density is 2770 kilogram per cubic meters. How do you determine the volume? Surface area times thickness. Surface area is 0.03 square meter, and thickness is 0.5 centimeters. We don't want centimeters, we like meters. So 100 centimeters is 1 meter. So 0.5 centimeters is 0.005 meters. So that's how you determine the mass of the system. So this mass goes in here. What is the specific heat? 874 joule per kilogram degree Celsius. What is the final temperature? 200. What is the initial temperature? 22. So we have everything but delta T. Can you determine how long it takes? Yes, you can. I don't know the answer, but you can calculate that, right? Any question about this problem? What? M is density times volume. So you can solve this equation to determine M. 874 is specific heat. After you practice this problem, one question you need to ask yourself: if I see this one in your second exam, can you solve it? If you are comfortable, if you have no difficulty, then you're good to go. If you are not sure, find similar problems in your homework assignment and practice again, and then come back to this problem later. Solve it again until you're 100% satisfied. Okay. One last problem before we finish chapter 3. We finish chapter 3 today. That means that there's a new homework assignment due by a week from today, Thursday, next Thursday. And please note that there are a lot of homework problems in homework 3. Very important. So I put a lot of problems in homework number 3. So please start solving those problems as soon as possible. Okay. All right, so let's go to the last problem of this chapter. Sounds like the hardest one in this chapter. On electronic device dissipating 25 watt. Again, what? We know that is not heat transfer. It is the rate of heat transfer. So you need to multiply by time to get the amount of heat transfer. 25 watt. So that 25 watt is going to heat this electronic device. So it will raise the temperature of this electronic device. And the mass of this electronic device is 20 grams, and a specific heat is 850 joule per kilogram degree Celsius. And it is on for 5 minutes. So the amount of heat transfer is going to be 25 watt times 5 minutes, during which it cools to the ambient temperature of 25 degrees Celsius. That means the initial temperature of this electronic device is 25. We want to determine the highest possible temperature of the device. So we want to find T2. But it says the highest possible temperature. It is not just highest temperature, highest possible temperature. Why it says the highest possible temperature? Because while the temperature of this electronic device goes up, since it is hot, the surrounding air is cold, so there's a heat loss to the surrounding. So when you see the highest possible temperature, when you have a very good insulation, trying to minimize heat loss from this electronic device, then you will see the highest possible temperature. So in mathematics, you can neglect Q out, then you will see the highest possible temperature. Okay, so based on that, let's write the energy balance equation. The energy balance equation is always the same. Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work. What is Q in? 25 watt. 25 watt is the heat is going to increase the temperature of this electronic device. Is that right? But now we know this is wrong. Why is that? Because it's power, it's not the heat transfer. So how can you convert this one into power? I mean, how can you convert this power into this heat? Multiply by the time. How long? 5 minutes. So you are going to multiply by 5? No, seconds. 5 minutes are 300 seconds, right? So multiply by 300 seconds. So that is the amount of heat transfer. What is the energy transfer by work? There are none. What is the heat loss? There should be heat loss, unless there is a significant amount of insulation. And we want to determine the highest possible temperature. That means that we have a pretty good insulation. So we will see how high the temperature goes up. So we assume that there's no heat loss. We have a good insulation. It's going to be mass times U2 minus U1. Now we know how to determine U2 minus U1. Cp T2 minus T1. So this Q is going to be mass times this one, Cp times T2 minus T1. What is the moving boundary work of this electronic device? There is no moving boundary work. Why is that? Because the volume does not change. The moving boundary work only exists when there is volumetric change. And what is the mass? 25 grams. Do you like grams? No, we prefer kilograms. 0.02 kilograms. What is the specific heat? 850 joule per kilogram degree C. What is the initial temperature? Oh, where is the initial temperature? 25. So what is the final temperature? Oh, that's what we want to determine. Now we have everything. Can you determine the final temperature? Yes, you can. What is it? If you do the calculation, you get 400. Where is it? 466. Are you okay with this temperature? Even in Kelvin, still too hot. 466 degrees Celsius of this cell phone. Not cell phone anymore. So that means your electronic device is not going to work. So we need to decrease the final temperature. How can you do that? Maybe you can, improve the cooling system, thermal management system. Like, the NVIDIA developing H100. Now they are using Blackware, using liquid cooling. Don't know that? So we can improve the cooling system, but it costs a lot of money. One simple solution is heat sink. Heat sink. What is it? What is heat sink? It's always easiest to use an example. So let's assume that you went to a dining hall and there was a bully. So this is my dish, and somebody put this much food, and then they ask me to eat all of them. Can you do that? No, I can't. So what I do? I couldn't eat all of them. So I'm going to, call my friends who is about this size and ask him, can you eat together? That's his sink. It's a bulk material next to this electronic device. So when temperature goes up due to heat transfer, some of the thermal energy is going to, increase the temperature of this bulk so that it limits the maximum temperature. It's a good example, right? Easy to understand. That's too big, right? Anyway, so what kind of heat sink we can use? This time 0.5 kilograms aluminum. So This is not an electronic device, just pure aluminum. Attach it to electronic device. So it's not costly, it's not expensive. It just share the temperature rise. Then how can you solve this problem? Now we have more than one system. We have electronic device, we have aluminum block. So the right-hand side is going to be two. One for electronic device, the other for aluminum block. So let me write the energy balance equation again. The left-hand side, we only have Qn. The right-hand side, now we have electronic device. Mass of electronic device, specific heat of electronic device, temperature T2 minus T1. That term is for the total energy change of this electronic device. Now we have aluminum block. Mass of aluminum, specific heat of aluminum, temperature T2 minus T1. So that is the energy balance equation when you have electronic device and aluminum together. Then what is Qn? 25 watt times 300 seconds. Mass of this electronic device, 0.02 kilograms. Specific heat of this electronic device, 850 joule per kilogram degree C. The initial temperature, 25. Mass of this aluminum, 0.5 kilograms. Specific heat of aluminum. From this table 19, 1819, aluminum specific heat 0.903, but this one has a kilojoule, so it's going to be 903 joule. Be careful about the unit. 903 joule per kilogram degree C. Initial temperature 25. So from this equation, we only have one unknown, T2. So can you find T2? Yes, if you do, 41 degrees Celsius. From 466, now 41. Can this work? Yes. Then we don't have to worry about the cooling system because the aluminum is going to minimize the temperature change as a heat sink. So that completes chapter 3. You have a new homework assignment, which is due a week from today, so next Thursday. And now we have a new chapter. Chapter 4, mass and energy of control volume analysis. In other words, open system. In chapter 3, we studied a closed system. Now in chapter 4, we are studying the other, the other system, which is an open system. So what is the main difference between closed system and an open system? What is the definition of closed system? Something is completely closed? Not necessarily. If you have air in this rigid container, yeah, that is a closed system. What about if it is, the open, the cup, and there's a water in it? Is it a closed system? Yes, it is a closed system, because the definition of closed system is mass is constant. As long as this water doesn't go out, it's a closed system. It doesn't necessarily to be completely closed. Okay? Then what is open system? It's simple. If a closed system means mass is constant, open system means mass is changing. So we have mass entering a system, mass leaving the system. So the simplest schematic of open system looks like this. We have an inlet, we have an exit. So inlet and exit. And since we don't have a constant mass, we are going to study this volume, that is control volume analysis. So open system is called control volume analysis. Closed system is called control mass analysis. Okay, this one is control volume. Then, what we want to study? We want to study always the number one, first law of thermodynamics. What is the first law of thermodynamics? Conservation of mass principle. You eat 3 hamburgers. You need to poop 3 hamburgers. Otherwise, you get fat. Right? So that's the conservation of energy principle. When you eat something and when you poop something, the remaining is going to be the change of the energy of your system. So that is the energy balance equation. Then how can we, apply this conservation of energy principle onto this open system? You need to, find how many energy transfers to this control volume, how many energy transfers out of this control volume, and the change of the total change of the total energy of this control volume. Then there's one the interesting thing is that the most open systems are steady state. So we're going to assume steady state open system first. We are going to study steady state open system. And at the end, one page, unsteady open system. So let's talk about steady open system. What is a steady open system? Yesterday, you were like, the 180 pounds. And today, you are 180 pounds. That's a steady system. But yesterday, 180 pounds. Today, 280 pounds. That's an unsteady system. That means, is there any change in the energy of your system? No. So what means the change of energy of your system? This one. So when you have steady state system, that means this one is 2, no 0. This is a steady state system. So no matter how much the food you eat, how much the poop you poop, the change of the weight of your body is going to be always the same. That is steady state system. So in that case, we just need to check how many energy transfers into the control volume, how many energy transfers out of this control volume. So let's think about the physics. What kind of energy transfer can you say to this control volume? We learned in chapter 2, there's energy transfer by heat, right? So we can say, oh, there's a heat transfer, Q. Or Q can go in and out, right? Heat transfer goes in, heat transfer comes out. Okay, no problem. And there can be energy transfer by work. Yeah, you're right. Energy transfer by work can go in, energy transfer by work can come out. Are they all, or there's more? Of course, there's more. What kind of energy transfer? What happens at the inlet? There is a mass goes in. if the control volume is about, let's say, 20 degrees Celsius, now mass goes in. This one is 1000 degrees Celsius. What's going to happen? The temperature of this control volume goes up because of energy entering the system, because of energy transfer by the mass entering the system. So when there is a mass transfer, there is energy, carried by the mass that goes in, that comes out. So there is one more energy transfer. Energy transfer by mass at the inlet, energy transfer by mass at the exit. By the way, in this equation, this one looks ugly. There's nothing on the right-hand side. So we can move this E out to the right-hand side. No problem. So I'm going to put this E out to the right-hand side. E in is E out. And we just found that there is Q goes in. There is a W goes in. There is an energy by mass entering at the inlet. So there's a Q goes in. There's an energy transfer by work goes in. There's an energy by mass that goes in is Q comes out. W comes out. And energy by mass at the exit leaves the system, leaves the control volume. So these are the energy, the balance equation. But there's something, we are not completely, happy about it, which is, I know what is Q, I know what is W, but what is E of mass? Have we studied E of mass? Yes. When? Chapter 2. What is the total energy per unit mass? This E is going to be mass at the inlet times the total energy at the inlet. W in plus Q in is Q out plus W out plus mass at the exit and total energy per unit mass at the exit. That's how we determine the total energy. Then do you remember this total energy per unit mass from chapter 2? Yes, there are 3 energies that become total energy. Internal energy U, kinetic energy V2 square over 2, and potential energy gravity times elevation Z. Do you remember that? Yes. So we can rewrite this equation as 2 in plus W in plus M at the inlet. This one has specific internal energy because this mass may have some temperature. This mass may have some kinetic energy. This mass may have some potential energy. Is Q out plus W out plus mass at the exit. This one has specific internal energy. This mass may have temperature. This mass may have kinetic energy. This mass may have potential energy. But that's not it. But that's not it. Let's talk about the inlet. Let's talk about this inlet. So this is room 128. Yeah, 128. So there's an inlet here. So ET128. So this door is open. Now there is mass entering this control volume. So this classroom is control volume. So there's a mass goes in. Can this mass just come in? It is completely vacuum, there's nothing inside. No, it is completely filled with our system, maybe air or water or whatever. So if another air, new air, is going to enter this control volume, what this air molecule need to do? I need to make my space. So push the air at the inlet, that means pressure, and create this volume so that I can walk in. So pressure times volume is the energy I need to provide into this classroom so that I can enter. So there's one more energy provided by the mass entering the system, pressure times volume. Took the mass out of pressure times volume, pressure times specific volume. Pressure times specific volume. That is the energy work that I need to provide if I want to enter this classroom. That's what you did when you entered this classroom? Yes, you did. But did you feel it? The energy? No. Why is that? Because this room was filled with air, which is compressible. So when you walk, you don't have to, you are actually pushing the air molecules in front of you, but you don't feel it because you are too powerful. You're solid. Pushing, the gas is super easy. But let's assume that this classroom is completely filled with students. There's another man or woman in front of you. Can you walk? No. If you want to walk, if you want to enter, now you need to push. So whenever you move, you need to provide this much energy, pressure times volume. That's what you do, but you don't feel it because you're much stronger than air. But when you walk in a swimming pool, now you feel some, some work. It's not easy to walk in the swimming pool. If you don't, try, the swimming pool in the sack. Jump in there, try to walk. That's what, the many, the grandpa and grandma do, in the morning when you go visit 9 o'clock. They walk to exercise. Why it is an exercise? Because it's not easy. In the air, it's super easy because air are compressible. But in water, water is incompressible. So pushing that water is not easy. The same thing here. So pressure times volume is the work associated with your movement, associated with your flow. Then, if there is a mass leaving the control volume, there's an exit. Let's assume that this is exit. Class is dismissed. You want to leave. If the hallway and the classroom is completely filled with the students, is it easy to walk out? No, you need to push outside. Push someone standing right outside. That energy is going to be removed from this control volume. I'm going to carry that energy outside. I'm going to, move that energy to the outside. So at the exit, you are providing this much energy to the outside. Pressure times specific volume. That is the energy balance equation. But when you see this energy balance equation, you may not be very happy because, oh, that's too long. So how can we simplify this energy balance equation? Let's think about, the property that we learned in the previous chapter. There was one property we learned. What is that? The new property, new thermodynamic property. Enthalpy H. What is the definition of enthalpy H? H is U, H is U plus PV. That is the definition of enthalpy. Let's see. There is a U, there's a PV. There is a U, there's a PV. So why don't we study U plus PV? That takes too much time because you need to, to find 3 different values. Instead, you can just say is 3 altogether H at the inlet plus velocity in square over 2 plus gravity times elevation Z at the inlet times mass at the inlet plus energy transfer by work and energy transfer by heat. What about energy transfer leaving this control volume? Q out plus W out plus M dot M at the exit. This one has enthalpy, kinetic energy, and potential energy. But there's one more problem. There are so many problems in thermodynamics. What is the problem? What is the difference between a closed system and an open system? Yeah, in a closed system, mass is constant. In an open system, you cannot say that because you have an opening, right? So, can you determine M in, M out? Some moment. Much easier if we use mass flow rate instead of mass. When it is a steady state, we cannot, determine what is the mass in the system, but we can determine what is the flow rate entering the system. So instead of mass, you can, use mass flow rate. How can you use mass flow rate? Divide by time, divide by time, divide by time, divide by time, time, and time. So the first thing becomes Q dot the rate of heat transfer plus W dot the rate of energy transfer by work, and M dot the mass flow rate at the inlet. This one has enthalpy, kinetic energy, and potential energy. And energy transfer out of the system, the rate of heat transfer Q dot out, the rate of energy transfer by work W dot out, the mass flow rate at the exit. This mass has enthalpy, kinetic energy, and potential energy. And this is the energy balance equation you are going to use in chapter 4 for steady state open system. Write it down on your formula sheet because you will use this every time when you solve any open system problems. That's the only equation you need for chapter 4. Then you may say, oh, this is a college class. Having only one equation doesn't make sense. So let's find one more equation. This m dot, how do we, what is this m dot? Mass flow rate. Then this energy balance equation is developed based on conservation of energy principle. There is another conservation principle that we know. What is it? Mass conservation. So we can apply mass conservation. M dot at the inlet should be the same as M dot at the exit. And this M dot can be determined by density times volumetric flow rate or density times average velocity times cross-sectional area. That's all. Not anymore. That's everything you need to know to solve any steady state open system. That's all the theories that you need to know in chapter 4. Then what we are going to do? We are going to solve a number of problems together to learn how to use these equations. We are going to solve these energy balance equations and mass balance equations for nozzles and diffusers. turbines and compressors, throttling valves, mixing chambers, and the final one, the final boss, heat exchangers. So we are going to solve, these devices thermodynamically. That's what we are going to do in chapter 4. And it's going to be easier to start with the easiest one, nozzles and diffusers. What is a nozzle? So let's assume that this is my backyard. There are grass, looks dying. They're all yellow. So what do you want to do? Or true green. Now I don't have money, so I'm going to water. I'm going to water this. The grass. How are we going to do that? I have a sprinkler. Now let's assume that there is no sprinkler. I only have a water hose. So what I'm going to do? Water your, the grass from all the way from here, and water your grass, and then go back, and then do this, the 200 times. That doesn't look like, the people studying engineering technology in this building. So what do? Instead of walking, you can squeeze the end of the water hose. What happens? Then the water velocity increases. So you can water the grass on the corner from here, squeezing the end. That is a nozzle. Okay? So why it happens? So let's talk about that thermodynamics. Nozzle is a simple device, has a large opening at the inlet. So I'm going to say inlet is number 1, and small cross-sectional area at the exit, number 2. Then there are 2 equations that we studied. The first one is energy balance equation. The other one is mass balance equation. Which one is easier? Or mass balance? So let's talk about mass balance. M dot mass flow rate at the inlet number 1 should be the same as mass flow rate at the exit number 2. Okay, that is the conservation mass balance equation. No problem. Then how can you determine this mass? Oh, here it is. Density times velocity times cross-sectional area. So I can use this one to solve for this m dot number 1. So this is density at the inlet times velocity at the inlet times cross-sectional area at the inlet should be the same as density at the exit, velocity at the exit, cross-sectional area at the exit. Now, what is the working fluid when you water your garden? Air? No, they drink water. So now we have water. Is it compressible? No, it is incompressible. That means the density at the inlet is the same as density at the exit. I'm going to cross them out. Then we have a large area, large cross-sectional area at the inlet. We have extremely small cross-sectional area at the exit. Then, to make this equation sign works, we should have small velocity, low velocity, high velocity at the exit. Because of this conservation of mass principle, if you squeeze the end of water hose, the water velocity goes up because of that. Any question? So that is a nozzle. Then how can you, solve this nozzle thermodynamically? That's no problem. You can use this energy balance equation. So I'm going to use this energy balance equation to study this nozzle system. So let's do that. When you use a nozzle, do we heat nozzle usually? We don't. Why? There's no reason. The nozzle displayed any heat? Usually no. unless whatever the working fluid is extremely high temperature. Does nozzle consumes any electricity, any work? No. Does nozzle produce any work, like the electricity? No. Is there potential energy change? At the inlet is on the ground, at the exit is on top of Mountain Everest? No. The potential energy change is negligible. How many inlets and how many exits? Just one inlet, one exit. So according to the mass balance equation, m dot at the inlet should be the same as m dot at the exit. We can just say m dot, m dot, m dot. So you can cross them out. So the energy balance equation is H in at the inlet is number 1, H1 plus velocity at the inlet square over 2 should be the same as H at the exit number 2 plus velocity at the exit square over 2. So this is the energy balance equation you can use for a nozzle system. Then do we need to memorize these energy balance equations for every thermodynamic devices? Nozzle, diffuser, turbine, compressor, etc., etc., etc. No, you don't. You just need to memorize this general energy balance equation, and you have your you just apply, you think about the physics and determine your own energy balance equation for each thermodynamic device. Yes.
Derive that by the situation, but could be still.
Then, yeah, you can do that, but you need to make sure, because sometimes, what about this water is at high temperature? Then maybe there is a heat loss. So you need to consider those, the special, the conditions. So of course, that you can use that one, but also you need to be able to, derive that equation, because sometimes there is a, the additional, the terms, like such as what if there is a heat transfer when the environment is at high temperature? Then you need to take those account. Then you should be able to derive those equations. Otherwise, you can only solve the very, very basic nozzle systems, right? Then, if you look at the title of this slide, it says nozzles, not only nozzles, but diffuser. So what is diffuser? Yeah. This is nozzle, this is diffuser. So it does exactly the opposite, the thing. So in nozzle, we know the velocity increases. Then diffuser, what do you expect? Velocity decreases. But there is another, the advantage of using nozzle. It's just not, the velocity, of course, velocity goes down, but because of this low velocity, the pressure at the exit is going to be low. The pressure at the exit is going to be low. That is the advantage of using diffusion. Think about this class, that this classroom is filled with 500 students. Then, wow, it's too crowded. So when you want to go out, it's not easy. It's not easy. You have a lot of pressure. There are so many people. But once you leave this place, then there is a plenty of space. So once you pass this diffuser, there's a plenty of space. So the pressure goes down because you have less materials at the exit. So we use this diffuser not only to decrease the velocity, but also to decrease the pressure. That's why we use diffuser. Then what is the energy balance equation? the same thing, the same energy balance equation for this diffusion. Okay? So that is the summary of the physics and mathematics. And based on this physics and mathematics, let's solve a few problems together. So here is the first problem. Air enters an adiabatic nozzle steadily at 300 kilopascal, 200 degrees Celsius, and 45 meters per second. Need a scratch paper. And it leaves at 100 kilopascal and 180 meters per second. We know the inlet area, and we want to determine the mass flow rate, exit temperature, and the exit area. Okay, let's do that. First, we need to understand the physics. So we have a nozzle, and we have inlet number 1, we have exit number 2, and at the inlet, P1 is 300 kilopascal. P1 is 200 degrees Celsius. And the velocity is V1 is 45 meters per second. And at the exit, the pressure P2 is 100 kilopascal, and the velocity is V2 is 180 degrees meter per second. So that's the physics. Then let's talk about mathematics. We have two equations. The first one is mass balance. M dot, the mass flow rate at the inlet, should be the same as mass flow rate at the exit. Okay. Then how do you determine this mass flow rate? Density times volumetric flow rate, or density times average velocity times cross-sectional area. That's the first equation, mass balance. And the second equation, energy balance. What is the energy balance equation? Assuming that we don't know, the general energy balance equation is Q dot in plus W dot in plus M dot at the inlet, number 1. This one has specific enthalpy, specific kinetic energy, specific potential energy, is Q dot out plus W dot out plus the M dot at the exit, number 2. This one has specific enthalpy, specific kinetic energy, specific potential energy, gravity times elevation C2. So that's the general energy balance equation. Of course, we are not going to use it. There's no information about heat transfer. It says adiabatic nozzle. What is adiabatic? There's no Q. There's no heat transfer. Q, go away. Is there any energy transfer by work? Does it produce any electricity? Does it consume any electricity or any kind of work? No. Here, ground, here, mountain evidence? No, there's no potential energy change. M dot is the same as M dot. M dot 1 is the same as M dot 2. M dot 1 is the same as M dot 2. So the energy balance equation is this one should be the same as this one. Then to make this one simple, so this one is H1 plus V1 square over 2 is H2 plus V2 square over 2. So why don't we move this kinetic energy to the right-hand side, this specific enthalpy to the left-hand side? Then we get H2 minus H1 is V2 square minus V1 square divided by 2. Sorry, I cannot see that. Then this is the governing equation. So let me write it here. H2 minus H1 is V2 square minus V1 square divided by 2. So these are the two equations. Any question up to here? So first, whenever you see a thermodynamics problem, first think about the physics of the problem. Based on that, come up with the mathematics of the problem. Then you are ready to solve this problem. Always remember, when you have a steady state open system, there are two equations: mass balance, energy balance. Mass balance, energy balance. So now you can solve this problem. Which one? What? Where? Oh, this one? Oh, I move this one to the left. Yeah, only these two survive. And I move this H to the left and velocity to the right. Oh, 6 minutes. So I need to hurry up. 6 minutes. 6 minutes. I'm going to put this one on top so you can continue, right? So let's solve the first problem, the mass flow rate through the nozzle. Where is mass flow rate? The first mass balance equation. How do you determine that? Density times velocity times cross-sectional area. Do we know the density? Oh, no. Do we know the velocity? Yes. Do we know the cross-sectional area? Yes. So if you know the density, you can get the mass flow rate. Do you know any equation that we use to determine density? If you're not, sure about density, then think about, the specific volume, because specific volume is the inverse of density. Do you know any equation that has a specific volume that we studied in the previous chapter? What equations did we study in chapter 3? The table, ideal gas, specific heat. Among them, anything has V? Yes, ideal gas. So what is ideal gas equation? PV is RT. This rho is the inverse of specific volume. So this one can be rewritten as, because this one is 1 over density, we can say this is P over rho is RT. Can we do that? Yes. Now, where are we going to apply this ideal gas equation? At the inlet or at the exit? You can only apply, the one state rather than mix them up, right? So let's apply this one at the inlet. P1 over rho 1 is R times T1. So what is P? 300 kilopascal. What is R? The gas constant of air. How do you determine that? Universal gas constant R bar divided by molecular weight. Universal gas constant is always 8.314 kilojoule per kilomole Kelvin, and the molecular weight can be found from table A1, 28.97. 28.97 kilogram per kilomole. But the gas constant of air is widely used. So you may want to memorize this number the gas constant of ideal air is going to be 0.287 kilojoule per kilogram Kelvin. We will use this a lot because air is one of the most widely used working gases in thermodynamics. So you can memorize that. And what is this T? Initial temperature, 200. So I'm going to write 200 degrees Celsius. Is that right? No. Kelvin. We all know that, right? 473 Kelvin. So from this, can you determine the density? Now, yes. Now we can determine the density. And let's, come up with this mass balance equation. M dot 1 is density times velocity times cross-sectional area. And here is the density that we calculated from this ideal gas equation. What is the velocity at the inlet? 45 meter per second. What is the cross-sectional area? 110 centimeters square. Oh, we don't like centimeters. 100 centimeter is 1 meter. And by the way, we have a centimeter square. Then 1 square meter is not 100 anymore. 100 square. 10,000 centimeters square. Then you get the mass flow rate. If you do the calculation, mass flow rate is, do I have it? 1.094 kilogram per second. That's how you determine the mass flow rate. The exit area, exit temperature. Unfortunately, we only have, the time is up. So we are going to, determine the exit temperature and the exit area next Tuesday. Any question about this problem? Only the first part. So on Tuesday, we are going to use this energy balance equation to determine the exit temperature. Once you determine the exit temperature, we are going to use that exit temperature to determine the exit area. Okay. So that's all. We will continue from here on Tuesday next week.